All right, hello everyone. So today we'll be going over a lot of the common convolutional neural networks, and those usually result from the Imagenet competition, since it's a very popular benchmark for most of the CNNs that we see every day, or yeah, usually. So it's Imagenet. So what is Imagenet? It was a large-scale visual recognition challenge, and it had a lot of data for over or about 200 categories. So, all the common objects that you see, like giraffe, airplane, cats, it contained all those objects with labeled data. And we stopped. I think it went on from around 2012 to 2017, and it stopped in 2017 because all the models were achieving over 95% accuracy, which is already better than how humans performed on the data set. So they evaluated the different models using two metrics. So you have the top one accuracy, which is how many times top predicted the class and matched the actual class. And then you have top five, which is how many times the actual class was one of the top five predicted classes. And the top five was an easier task than top one, since you just need at least one of them to be the correct one. Anyways, next slide. And I think one of the main most famous ones that came around first was AlexNet. And so this was named after Alex, which was the first author of this paper. So it started off very simply with 8 layers and 5 convolutional layers with a max layer in between, or max pooling, sorry. And as you can see, it's very interpretable. And you had your fully connected layers at the end. And this achieved a 15% error rate on Imagenet in 2012. And of course, it won Imagenet in 2012. So nowadays, this isn't very novel, but at the time, it was very novel because this network used ReLU. At the time, a lot of people used TANH and sigmoid, which meant that it was possible for a lot of explosive or vanishing gradient problems to occur. And also, ReLU made converging a lot faster. So AlexNet also used dropout. So that was a question we had in the Kahoot, where you can remove a percentage of a certain neurons and you determine the percentage to reduce overfitting. And the author of AlexNet, the first author, was actually also the author of Dropout, which I think is really interesting. And AlexNet had around 60 million trainable parameters, which would have had a lot more problems with overfitting if it didn't use the dropout techniques and ReLU. Next slide. So after AlexNet, actually a few years after AlexNet, we have ResNet. So ResNet is named after, the res in ResNet is named after residual connections. And this one in 2015. So there was a problem where, in general, CNNs have a problem where if you keep on stacking more layers, that doesn't necessarily lead to a lower or a better accuracy or lower error. So the motivation with the ResNet was to see if, they could find some sneaky way to keep on adding layers without it having to overfit. And ResNet used a lot of novel techniques as well, such as Xavier initialization and batch norm, which we discussed in a previous workshop. So continuing on. What was special about ResNets was that they had something called residual blocks. So basically, this allowed it to be able to learn the residual, which is basically, I believe, the the difference between the input and the output. And based on, mathematical theory, apparently that is easier to learn in some cases. Um, and this allows it to propagate gradients faster. And also, like if you look at the structure, this kind of has this would look similar to LSTMs if you attended our previous workshop, where it kind of sometimes passes on a value to future layers, which kind of allows us to skip training certain layers. And this is kind of based off of highway networks, which I'm not that familiar with, but if you're interested, take a look at that for what inspired ResNets. And yeah, we also have MobileNet. So this is kind of a little different, but their architecture is more designed for mobile devices, and it's more lightweight for reasons that I'll go into later. And it also has a smaller model size and it's more easily tuned because of that. So we go to the next one. And the reason why MobileNet is good is because it uses a different kind of convolution called Depthwise separable convolutions. So in normal convolutions, if you remember, we have to apply a kernel and perform matrix multiplications on all of the usually 3 channels at the same time. And then we get to our final output size after that. So for depthwise separable convolutions, it kind of separates that step into just calculating, doing convolutions like through the channels and then doing convolutions pointwise. And then at the end, it has the exact same output size, but it just reduces the number of multiplications that you have to do. So for instance, in normal convolutions, you would have the final output size of a depthwise convolution in one step, but that requires more multiplications. And then so what this convolution style does is that it separates it by calculating it, it calculates it channel-wise first and then point-wise. So kind of individual channel-wise, which is, go to the next slide. So you can kind of consider this optimization as kind of similar to spatial convolutions, which is where you take a matrix and you reduce it to a multiplication of 2 different matrices or vectors. So it's kind of similar to like that kind of optimization, but we don't use this one specifically for convolutions because not every matrix can be reduced in this way. The matrix has to have a special property to be able to be reduced in this way, which is why instead of this, we use depthwise separable convolutions. Yeah, so next slide.
Okay, so this is one of the more old networks that was created. I think it was created in 2012. It's called VGGNet. And so what's really unique about VGGNet was that it's really large for its time. Although it only used 3x3 convolutions throughout this whole network, it was still really large because it was like 16 layers and had like, I think around 80 million parameters. And this 80 million parameters just comes from like multiplying all of these values by each other and multiplying this, and yeah, there's like 80 million of these. And then how, like the most interesting feature is probably how quickly it actually reduces the dimensionality of the input. Like we can see that it starts off as like a 224 by 224, but like really quickly it just drops to 112 and then 56. So it's like takes the half of the size of the input each time. So it like really rapidly decreases as opposed to a prior network, which the prior network such as AlexNet, which doesn't actually reduce the image features as rapidly, because you can see that it first does from a 224 to 55 by 55, and then just like slowly slows down after that. And also it uses like different convolution sizes. That's like another difference from VGGNet. And so since it was like really large for its time, it used a method called pre-training, which initializes parameters for larger networks, which like you just like train a smaller subset of the network and use these pre-trained values as the initial parameters for a larger network. And this isn't used anymore in networks that we train currently because it's been replaced by Xavier or Glora initialization, which we talked about before in a previous workshop. And also for VGG specifically, network initialization was actually really important, as if you get like a really bad initialization of the parameters, it sometimes will not converge. That's like kind of why they needed to use pre-training. And the other thing that was unique about like VGGNet, like all of these papers, like all of these networks are proposed by like some paper. So what's cool about this one was that they actually made multiple different configurations for VGG, like VGG 16 and VGG 19. They all have the same overall idea, which is like this really quick decrease in complexity by a factor of 2. However, what's unique about them is the number of, I guess, convolutional layers after a certain period. Like as you can see, like VGG11 is used as like a pre-initialization for the other ones, and so is the C configuration, which is used as a pre-initialization for D. So there's like a lot of like pre-initialization that goes along just to speed up the input and also to help make it converge faster. But then like the other cool thing about this type of network configuration is that they always use the same max pool and the same fully connected layers at the bottom. So like from these type of diagrams, it kind of like sums up all of what we've done throughout this workshop, which is like from these workshops, you can probably understand what all of these different symbols. Yeah, symbols mean. Like this just means convolution. This means max pool fully connected. 4096 means that this layer has 4096 neurons, and this is the size of the convolution, and this is the number of filters there are in that specific layer. So like if you were to implement this into an actual neural network, you would easily be able to do this just by importing like convolution 3 by 3, and 64. So like that kind of just looks like this. And so then the next network that was really cool, or like really state of the art for its time, is called Inception. Inception was made by Google, and the most prevalently used one is Inception v3. This one's much more computationally efficient compared to VGG. However, because of how fine-tuned this network was, it's really difficult to adapt it to new use cases. To new use cases. So since like this network has like a lot of like specific features that are really specific to the Imagenet problem, which is like that 224 by 224 by 3 image, and all of these network layers are really fine-tuned towards that. It's really hard to use this for different tasks, such as like a 32 by 32 input image instead. And so what's unique about Inception and like the uniqueness, like the unique parts that made it so fast, was that it used factorized convolution, which is essentially, instead of taking like a 5 by 5 convolution, use two 3 by 3 3 by 3 convolutions, which has around the same performance, but has significantly less parameters, because this one has 25 parameters, whereas this only has 18 parameters. So like these small kind of fine tunings will make like really big difference overall, as it'll just like speed up the overall network. And there's also, and like based on that, they also use something called asymmetric convolutions, which essentially just splits this 3 by 3 matrix or filter into a 3 by 1 and a 1 by 3 filter, which train much faster, as like you kind of see here. This is like a 3 by 3, and then they would just split it into like a 1 by 3 and a 3 by 1, which is like supposedly faster. And then the other thing that was unique about this is that they have like this auxiliary classifier, which is like a small CNN that's inserted between layers. And then what this basically does is that this is like basically trained at each time step, and then the loss of this is added to the main loss. And what that allows you to do is that it just like makes it much easier to like compute a good loss and to be able to figure out what hyperparameters you should tune. And the last thing is called grid size reduction, which is so in prior papers like in VGG, they used a max pooling layer along with a convolutional layer to address the issue. Well, they're done like sequentially to address this issue of decreasing dimensionality. But in this paper, they propose to use the convolutional layer and the max pooling layer together. And as a result, this actually like speeds up computation also. So like as a result of that, like this is like the mess of a network they have. It's like giant. And it's really hard to like represent in like a really neat picture like this one, just because of how convoluted it is. I get it. Yeah. And then this is like an overall network comparison between all of the performances on the Imagenet competition challenge. So kind of like what we can see is that ResNet was like huge compared to the other ones. It had 928 million parameters, and however, its accuracy is like really good, 97% accuracy on the top five, and top one at 85%. And then you can see that like VGG was made in 2014. It had 144 million parameters, but it had the same performance as Inception, which was made 1 year later, but it has like a whole magnitude less parameters. So these parameters are really important because the less parameters you have, the more efficient the model is. In other words, it takes less space to store and also is quicker to train. So ideally, you want as less parameters as possible while having as high accuracy as possible. So like you can see with DenseNet, that's 94% accuracy and a little bit more parameters than Inception. So Catherine, do you want to talk about transfer learning?
Yeah. So transfer learning is basically where you can take a network that's already been pre-trained, let's say on Imagenet, and then you can train that on your new data set that's completely different. Yeah, so you can use like ResNet, VGG, and then all you have to do is add a new fully connected layer or retrain the last fully connected layer at the end with your new data set. So what this does is that, well, first, for first for you, you don't have to kind of like code the network from scratch yourself and kind of have to go through the entire training process, because you're just retraining or remaking the last fully connected layer. And also, you just don't have to like code the entire model from scratch again. And then also you can achieve some good results on the same task, essentially in a new setting, since the network has already been pre-trained with those features. And yeah. So actually there is a really nice resource for you if you wanted to get into transfer learning. So TensorFlow has kind of like a model zoo where you can access models that have been in Imagenet that are pre-trained. Actually, I can just send it in the chat. It's really nice. Yeah, so you can go to like TensorFlow Hub and access these models, and it contains like all the feature vectors. So basically what you do with these models is that you still define like your data set with its individual labels and everything, but you can retrain this model on like your new data set. Yeah. Edward, would you like to take it away?
Yeah. So like one of the key takeaways for transfer learning would just be that the perks of it is that you don't have to actually train the part that's already been trained. Like I just want to emphasize that. I think Catherine already mentioned that before, but by not training the parts that's already been trained before, like you don't want to like retrain all of like ResNet or something with 928 million parameters, because that's going to take like, I don't know, like a week to train. So as a result, by using transfer learning, you just don't have to train that part. You can train like a couple layers at the end, which is significantly faster. So now we can just go ahead and like actually like do a live demonstration of how we're going to actually make a convolutional neural network. And I think I have it somewhere. Can you still see my shared screen?
Yeah,
Okay. Wait, what do you see right now?
the slides.
Oh. Okay. Okay, we'll go here. So
Okay, gotcha.
I've already what's it called? I've already initialized. Is that the word? Initialized? Yeah. Okay, call it initialized. Let me just pull up this. This is like what we're gonna. Oh wait, no, that's tracking. No, not that. Okay, so the goal is to make something like this one, which is like just like a kind of like a network that we're gonna make ourselves. So this is like the first step, which is like import TensorFlow, because we're gonna have a workshop on TensorFlow and TensorFlow Care specifically later on, just to show as to how we actually use Keras. And so like the first step would just be to actually import the data set, which is CFAR10. CFAR10 is another competition data set, which is significantly smaller than Imagenet. It's in Kaggle. Yeah. Kaggle has a lot of data sets. That's the thing. So in order to do that, we just do this. So TensorFlow has a really neat way to where it stores the data sets inside like datasets.cfar load data. And then you do train images, train labels, which is, because this is a classification task, you just get the train images and test images for the result. And then you'd have to divide this by 255 because the input is, the input parameters are like a, I can just print one out right now. The input is like a really weird dimension where it's like 255, but to speed up processing, if you just use instead between 1 and 0, it's much faster. So like as you can see, this is like the first image, and then by dividing it by 255, you just get like really low numbers. Like before that, this would be significantly larger numbers, which are harder to compute on. Like this is like big numbers. And neural networks, as we mentioned before, neural networks work really well between 1 and -1. So that's why doing this by divided by 255 is a really effective tool. So the next step in this process would just be to kind of define the input shapes themselves. Can I delete this? Oh, I can delete this. So first, in order to make the classifier, we had to figure out the sizes of our inputs. So in order to do that, the easiest way is to just do, because this is TensorFlow stores it in tensors, but this is stored as a numpy array. So I think you can just do size, no? Yeah, I think you just do size. And then it should show, oh, not this one. Is it size? No, is it dimensions? Wait, what was the command? I'm pretty sure it's dimensions.
Is it shape?
Yeah, wait, I meant shape.
Yeah, it's shaped.
Yeah, so shape. And then you get, I think it's 2.8. Yeah, it's 50,032 32 by 3. So this is like the high length and width. And this is the number of colors in the picture. So 32 by 32 by 3. So the input for this would just have to be a 32 by 32 by 3 input. So let's do that. You just do something like this. Train images equals, I know. Yeah, okay. I think there was some specific thing about this. No, I think it's fine. So we can just start coding the model itself. Model equals models.sequential. What sequential does is that this makes like a quote unquote sequential model, which is a model that is just completely linearized, like as you can see here. It's going to look like more like a just completely linear model like this, which is why you'd use sequential, because it's like in a sequence. For networks like this, you'd have to do it in a different way in which you actually define the inputs and outputs. So this is models.sequential. This will just like create a model, kind of a model class or whatever it's called. You know what? Okay, I'm going to assume it ran. I think it ran. Okay, and now all I have to do is define the input shape. Or the first thing we'd have to do is add the first convolutional layer to it. So I guess we can for now just emulate VGG16, and like the overall idea which is to have a 16 weight layers, 2 convolutional layers, then a max pool, then a convolutional 3 with 128 neurons. So we can just like kind of model this. And so yeah, we can just start. So model.add, the first layer we know is going to have to be a convolutional layer, as we can see there. It's going to be something like convolution 2D, 32. I think I'm forgetting parentheses, but it's fine. I'll figure that out later. By 3. And then the activation for this is ReLU, because in the paper, they said, yeah, convolutional plus ReLU. So you do something like activation. No, I need the parentheses there. Activation equals ReLU. Yeah, and this is the first layer. You need to define it as, you need to find the input shape. And since we know the input shape is 32 by 32 by 3, and since it's actually outputting this whole mess of a thing, all we need to do is we can just define the input shape as something like this. So we can just do 32 by 32 by 3. And by running this function, it'll just create the input. Oh, kernel size. Yeah, you just put a comma there. And then it's the kernel size. I think that fixes. Oh, it doesn't fix it. You know what? Screw it. 50,000. Or no, I can just put 1. Because we're gonna feed it 1 by it. 1 by 1. Sus. Okay, wait, what was I doing wrong? I'm pretty sure this works, no?
Edward, line 1. Sorry, com2d, you have open parentheses 32, close parentheses. That's only for filters, not kernel size. Do you see the parentheses is broken?
I forgot to close the parentheses. Okay, there's some other parentheses I'm missing. Oh, there you go.
Yeah.
Okay,
There.
so
Okay.
now the layer has one thing. Thanks, Jonathan. Okay, the next step would just be to make another layer. This is a 32 by 32, which is yeah, we can just do 32 by 32. So what 32 by 32 means is that this layer has 32 layers in the first one. So now we can just add another one. So adding layers using sequential is really simple. You can just do the same thing again, and that'll give you another layer. And this one, let's do 64 by 3, 3, activation. Activation equals ReLU. And so this is just going to add another layer to your model. And what's really neat about this is that you can actually see your output in real time. I think we talked about this before using model.summary, but yeah. 64 is the number of kind of filters or the number of neurons in that layer. And then, should I actually follow VGG? I feel like I should just follow VGG for this one. Yeah, okay, never mind, I should just use 64 then. VGG Imagenet is 224 by 224, but this is gonna be kind of difficult. It'll be fine. It'll have like some not as optimal performance just because it's fine-tuned on a different, or the configuration only works specifically for that type of thing. Max pooling 2D. So what this does, as we kind of mentioned before, max 2D will just make a max pooling layer, which is the whole purpose of this is to just reduce the complexity of the function by, or reduce the size from like a really large 32 by 32 by 3 into something a little bit smaller than that. And so we can honestly just run it at this point. So since this is a classification issue, we need to flatten this out by using just a flatten layer like this. Yeah, so now this just flattens this input from, I think it was, I think it's be like some 49 times 3 by 3 input into like a 1-dimensional array, which then we can plug into some dense layers, which is going to be used as our final classification. And we don't want like a really large drop from all the way from like a really like 1,000 parameter input all the way up to like a 10 parameter input. So we do something in between, which is just using the dense function, like let's say ReLU. And yeah, did I run that? I'm pretty sure I ran that. Okay, I'm gonna assume I ran that. And then the last one is just gonna have to be softmax because softmax outputs probabilities of relative to how many different inputs there are. So we do something like layers.dense. There's too many. Okay, it's fine. 10 activation equals softmax. And so this is just like our whole layer. And then if we want to just like view the layer itself, we need to just first compile it. And then after compiling it, we can actually view the whole model. So usually we use Atom as our compiler because Atom is the best for most tasks. And then for our loss, we need to use sparse categorical cross entropy because this basically takes categorical cross entropy essentially outputs category-based losses, or it's like the most commonly used classification for most commonly used loss for classification. Yeah, and then you use accuracy as your metric, and then you can just use model.summary to actually view your model. Model.summary. Do I have to? I'm pretty sure I don't. So now, yeah, so this is our whole input. And so as you can see, the model parameters get really high really fast. Like this is already at 800,000 parameters. Like this is starting from a 32 by, this reduced the 32 by 32 by 3 input into something like this, and then further got reduced. And then yeah, so this is from this to this, you just multiply it by the number and you get this. So first we can just train this honestly. Let's just try that. So in order to train using Keras, we just do model.fit. There's another one not using fit, but I like using fit, so it's fine. Train images, train labels. This is the trained images, this is train labels, and we need to do it in this format because the input of this is going to be the input of this is images, and the output is going to be train labels. Oh yeah, I should probably show what train labels looks like. So print train labels dot size. No, it's not size. What was it?
Shape.
Oh, yeah, I meant shape. Yeah, so this is like a 50,000 by 1. And what this means is that each class only has one output. And so what categorical cross entropy does is that it just compares the probabilities that are generated with the correct one from here. So now we can just do the model.train stuff. History equals model.fit. So model.fit will just like do the whole training process for you. And it's really a neat feature. And then we can train it for 30 epochs. And you can also have validation data. TensorFlow splits its data sets into only test and train. It doesn't really have a validation one. But for our purposes, we can just do this. And then, yeah. So this should just be running the model. And I think it should be running pretty fast, actually. So you can see how the accuracy is going up as we train it. We don't necessarily need dropout for this one because our network is pretty small. And we're gonna start having to add dropout in other layers to kind of like fine tune the network to see, just to like get a little bit better performance. We would use dropout. So we had like a slide about optimization, which is if the model has like lower cost on training data than testing data early on, we likely have overfit on our training data. Yeah, 822K is kind of small because.
Wait, Edward, did you turn on GPU? This can take forever.
Wait, how do you turn on GPU?
Oh, okay. Don't do it now. But you have to restart it. You have to restart it if you want to turn it on. But if you click runtime at the top.
What is this?
Change runtime type. Yeah, you can select GPU from here, but like it's gonna restart the whole thing, so don't do it.
Okay. Yeah. Wait. Yeah. Honestly, 822K is pretty small because like this really simple network is 822K, but these are like a whole like 10 magnitudes, 100 magnitudes higher. This is not my PC alpha. This is Google Collaboratory, which I kind of highly recommend because Stone Token is good. Yeah, this is gonna take a long time because each of these epochs runs for 2 minutes. So I should probably just use the GPU at this point.
Wait, why don't you add more pooling layers so you can just at least reduce the number of connections in your dense layer at the end?
Or I can just run it for 5 epochs. I mean, I could add. Yeah, let's just add more pooling.
Can you also batch it? If you batch it and you decrease the steps per epoch, it'll be faster.
That is true.
Yeah.
I think that's just.
Do you want to explain batching? I mean,
Okay.
I think we've explained batch graded descent before, but like this is similar.
So batch size just means that instead of taking one input at a time, it's going to take multiple input, and as a result, it'll be faster. That's like my understanding of batch. It's not like a complete understanding. Yeah. Wait, Stone, do you want to explain it?
Yeah, so usually like with normal gradient descent, you actually train over all your examples. So you take the sum of all your loss, you take the sum of all your gradients and apply them. With batch, you apply the gradients stepwise. So you apply the gradients. So for example, if our batch size is 32, that means we apply gradients for every 32 examples we get. So does MobileFit do stochastic by default or over all the data on the epoch? I actually think Model.fit by default sets a batch size of 32, so it actually doesn't do online learning or it's 1x1.
Yeah.
Okay, Edward, if you want the epochs to run less, you can do steps per epoch, just like cheese it a bit.
No. Yeah, so
Okay.
this is going to take a while. Or we can just do 2 epochs. No, that's a little too small.
Maybe we can talk about the rest of the stuff while it's training. But you see, like this is training really slowly. Many reasons. One, I don't think Google Colab gives us like a lot of resources anyway, but it gives you more. I think it's stronger than Edward's computer anyway. But the other thing is, you'll notice that we have 800,000 plus parameters. That's actually pretty hard to train, actually. It's pretty common to have that many parameters, but it's not that easy to train fast. The other thing is you want to note that convolutional layers are very expensive. This is why a lot of networks also use max pooling or some kind of pooling to reduce the dimensions very fast. So you see that in our model summary, when we reduce the dimensions from like 28 by 28 to 14 by 14, that makes the number of parameters and calculations needed for the next layer much smaller. Like without max pooling, that flattened layer will have, I think maybe 4 times more parameters, which would make it a lot slower. Yeah. So this is also why a lot of network architectures also stick in max pooling layers between conv layers to reduce the dimensionally faster.
Yeah.
Any other comments, Edward?
I want to use the GPU just so I can show the next step, but I didn't expect it to be this slow. I actually feel like my computer is faster than this.
David, yeah, Dropout should speed it up, not because of fewer params, but because they're more zeroed out. Because of more zeros, you're going to have a much more sparse matrix, which is faster to train on. Or a sparse weight matrix.
Okay, you know what? I'm bored. Let me just erase.
Daniel is asking, convolution layers, if you have like 30 neurons in a layer, does each neuron have its own kernel that's trainable? What do you mean by kernel? Do you mean kernel for a convolution? Oh, convolutional layers, my bad. Convolutional layers don't have like quote unquote 30 neurons per layer. What the neurons in convolutional layers are actually all the filters. So remember we have like X number of filters and each filter is like some K by K size. The weights of that filter is our neurons effectively. Because we're only updating the weights in a filter and every neuron is associated with a weight. So yeah, so the way convolutional layers work is completely different from dense layers. But this is also why I mentioned the Kahoot. Why convolution layers are pretty powerful is because one, they learn localized features. Two, to learn those local features, it requires very little parameters.
I thought it was 28 by 28, but I guess it's 32. Huh, interesting.
What do you say, Edward?
I thought what's it called? I thought CFAR 10 was 22 by 22. Guess I'm wrong.
Oh, the inputs?
Yeah.
Okay, Daniel, wait, let me go find some pictures that are helpful. I'll send them in Discord. Give me a sec.
Oh, I got it. I got him.
What'd you get?
The pictures.
Of the filters?
Yeah.
Okay, yeah, so filter, okay, well, I can explain a little bit. Filters are basically the kernels. Filter is like, it's typically a square matrix, basically, containing values to multiply things by. So you see that for when you have image data, let's say you're given grayscale image data that's 32 by 32. And let's say you have a filter that's size 3 by 3. That filter will have a depth of 1 because the image data you're given has one channel. Filters and kernels are the same. Oh, sorry. Yeah, filters and kernels are the same. Yeah, that's why it's called kernel size. And when we say by number of filters, it means to apply that kernel effectively 32 times. So you'll see, I don't have a good image. Does someone have a good image?
You want this one?
Wait. We want to show the other, I want to show another one. So if you have 32 filters, what happens is if you have like input with like one channel or, so okay, here's another common term for images. There's something called channels. A grayscale image has one channel of a grayscale value. An RGB image has 3 channels. Typically, what we will do is we'll expand those channels into more channels using the number of filters. So you train each of the values in a kernel, right? Yeah, each of the values in a kernel are weights. We train those.
So my computer is about as fast as Google Collaboratory. Interesting.
Well, at least you can share a screen without it dying.
I think my computer is actually dying though.
How?
It's lagging.
Okay, wait, Daniel, I'm gonna send something in Discord. Let's see. Just go check the Discord. I'll put it in
Oh my god.
resources.
Yeah.
Let me see if I can explain this.
My
Okay, do you see
computer is
this?
dying.
Daniel, do you see the image in Discord?
Yeah.
Okay, so this is very confusing, but basically, dn is the number of channels in input. So dn would equal 3 if you're given RGB images because there's 3 channels, red and gray and blue. If you're given grayscale images, dn will have dimension 1, which will equal 1. hn, wn are just the height and width of the images. So in our example for our data set was 32 by 32. And our dn, our data set is actually 3 because we're using RGB data. So now the next thing you notice is a variable called df. df is the number of filters. So each of those things, each of the little colored filters, each of them have different sets of weights, creating df number of feature maps. Let me see if I can explain this. So, so you see in our example for our ConvNet, we use 32 filters. What that means is we have 32 different kernels with different weights. Each of those has to be trained. And yeah, and when we train each of those kernels applied to the image gives us that giant box on the right of the image. And that box on the right is effectively our feature maps. These are features extracted from our input images using our filter number of kernels or filters, you can also call them. I don't know if that helps it anymore.
Yeah, that was helpful. Thank you.
All right.
What if I did this?
Okay, did it finish?
No.
Okay, it's almost there.
Wait a minute. Can I do it? Can I run twice? Oh no, this is.
Are you running it twice? Wait.
No, this is not working that well. Let's screw my computer.
Okay.
Yeah, this is just So what I want to show is that like you can like graph out the progress and then just use like the kind of like progress bars to interpret how you want to like change your model later on to have better output.
This is like the hyperparameter tuning we introduced like a couple weeks ago.
Yeah. So that makes
where we
sense.
want to talk about like overfit, underfit stuff.
Yeah. And so these are like the resources for all of these papers. There's like a lot of different there's like a lot of different networks for the ImageNet competition. They have like a really large like just diagram to show which ones. Oh wait, Hausu. Wow. Hausu is a professor at UCSD. Oh no, I can't find it. But there's like a really large diagram that shows like how well all of the different networks are preparing in like some graph. Can't find it. Oh, there we go. So yeah, this is like how well they're doing. This is not the really good one. This is a really good picture. I can't find it. Unfortunate. Oh well, that's fine. I'll find it and then just post it in the chat. So there's one that just shows how all of these papers are essentially performing on this task, and it shows like how progress has been gradually getting really good. Okay, now we can just wait until this is done. Wait, Alvin, do you want to talk about stuff?
All you, bud.
Oh. Yeah, so this is gonna take some time to train. It shouldn't take that long though. Yo, this is only 822. And also 822 is just like parameters. Like imagine this as like just like multiplications and adding values. So this is like not that big of a issue because each of these is like a tensor, and each of these tensors you just do some multiplication stuff on it, and it doesn't really take that much. Each one doesn't really take that much computational power. It's when you get into stuff that are in the millions that it kind of gets kind of iffy.
No, I think it's really just you put two convolutional layers together, or like you have a 32 filter input, 32 channel input from the first conv layer to the second one, and then you're producing 64 filters. So each of those filters have to be size 32 by 33 by 3, which is why you have like, and then like sliding window across the whole thing is a lot of multiplication.
That is true.
Yeah. But if you're Google or something, you have the money to run that. So
yeah, because usually the networks, or at least what I've seen, is that they always do the two convolutional layers at the start together.
you gotta have a beefy computer and GPU.
Yeah, that's like the main conclusion here. Yeah, they have multiple convolutional layers. They have one.
No, they have max point between the first layer and the second layer for
That is
AlexNet.
true. Well, VGG does not. Not like VGG.
Well, VGG is crazy.
That is true. So yeah, we can just wait until this trains. This is taking like 2 minutes. Also, TensorFlow has like a really good transfer learning module also, where all you have to do is just I forgot the exact command, but you can just directly input TensorFlow transfer. TensorFlow. Let's do. I think they even give Inception. No? TensorFlow Inception. Yeah. You can just instantiate the Inception model just by doing this, and you can have this as your model. What's your main focus for today? Is this like that? Oh yeah, it is the background. I'm not sure what the background is actually. I forgot. Thanks, Jonathan. Hey, Catherine, do you have anything you want to add?
I think your model is close to finish training.
Thanks.
Nice.
This is something you can do if you're training a model or something. While you're training it, you can like do exercises, so it can be a healthy data scientist.
Oh my god.
Have to stay healthy people.
Yeah. So what's really good about this is actually how. No, JK, it's not that it's like okay, like it kind of makes sense. The validation accuracy is lower than the test accuracy, but it's not that bad. And both of them are still increasing. So what we kind of know about this is that one, we can either train it for a much longer time. Yeah, so I think the best approach for this is just train it for a much longer time. And if it sees like if it's like asymptoting, then maybe we can actually like add more layers or something like that. Yeah. So yeah, that was like, oh wait, I should probably share these slides. Oh. Editor? Yes. Okay, go nuts with the slides. Servers. Servers are the way to go. If you can get access to a server, then you can train it. Honestly, you can probably train. Like I trained VGG multiple times on my own computer. I don't know why, but I just did it. Haha.
Oh, it's finished.
Wait, well, why is this over here? Can I move this? Yeah, I can.
Just click the plus. Oh, okay, yeah. You can click plus code.
Yeah, and then now you can actually plot this out. I should probably have imported.
Wait, Edward, you enabled edit access on your slides. What the heck?
Yeah. Collaboration.
No. What? No, you don't want people to edit the slides.
Collaboration.
Oh my god.
Okay, fine. There's a new link. Just use the new link and not the old one. Oh, I forgot to import NumPy. Oh no, I want to import matplotlib actually. Matplotlib. This is like a really common thing to do, where you just like plot out your matplotlib. Oh, no, they did already. Did I do it already? No, I did not do it already. So if you do this, you can actually like plot out the network, and it can actually figure out how good your thing is. Yeah, just like don't do like weird stuff on the slides, and then I think you'll be good. So now if you actually print out the history thing, this is actually a dictionary of all the values. So this is like the callback, it's like an object. And you can actually access this by doing something like this. Print. I don't know why, but if you do history.history, you actually get all the values like loss, accuracy, validation loss. So you can actually plot all of this data out onto a matplotlib plot. And using that, you can actually tell how well your thing is doing. So I could just do that right now. PyPlot, history.history, accuracy. The other thing is that between TensorFlow 1 and 2, they changed the names or something, and it's really annoying. Accuracy, should I put a label? I'll put a label equals accuracy. So that will add, yeah, so that's how it looks. That is the accuracy. And we can do the same thing for validation accuracy. Like this. Run it? Yeah. So yeah, validation accuracy was more bouncy around, which is probably due to, well, it's probably going to look more like better if you just have more input and you run it for many more epochs. So yeah. Also, you can test your, like after you like do a lot of stuff and you don't want to like actually, if you want to test it on like individual inputs, you can do something like model.evaluate, which will evaluate it on like a single image. So if you do something like test images.0, this will evaluate your model. Aha, test images. This is dimension. Yeah, I need to reshape this. Reshape into, yeah, that's the issue. Nope, that is not the issue. I'll just do batch one. Yeah, it says. Oh, wait, is your accuracy of the training set or? So that's due to how the data set is processed using TensorFlow. TensorFlow automatically divides it into train test and test set, where train test is 50,000, where the training set is 50,000 images, and the test set only has 10,000 images. So for these, they've already like done it for us. So when I actually like fit the model where train images, this is only using the 50,000 images from TensorFlow's 50,000 data set, and the validation accuracy is on the test ones. Yeah, so we technically have to break up the data ourselves. Yeah, this is kind of bad though.
Wait, show the first image. What is the first image even?
This one?
What is the first image? Test image 0. Like, can you do like the CV2 image show or something, or PLT image show?
Okay. Import CV2. I think it's CV2.
Or you can just do PLT image show.
Import PLT dot image show.
Yeah, it's IM show, I think.
Train images dot 0. I think it'll give.
Wait, what is this?
I'm not sure.
Wait, what's label 0 meant to be?
What? This one? Like 1, 2, 3?
No, what's the actual, like, what's the label of that?
This
Do we
one?
have it? Do you have the test labels?
Oh yeah, I do. I think
But
it's
wait, the
not
test
right.
labels are numbers though, right?
Yeah, but I think you can directly correlate number to that
Do you have
one.
a name?
I think it's in the data set itself. So look at Kaggle. Haha. Oh my god, what is the dimensions of this? Oh no, wait. Test labels 3. Print test labels 3. What? Is it all 0? Kaggle. What is this? C part 10? I'm not actually sure what it is. Data. What? Wait, I'm pretty sure it's I don't think it shows what the label is.
Let me go
Yes.
find it. I can find it online.
Wait, what is it? CFAR 10 data set.
It's airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck.
Yeah, so let's try classifying it ourselves. Training. So yeah, let's take some time to look at. I think this is an airplane.
Is that an airplane?
I think it looks like an airplane.
I really can't tell.
Is it a bird?
Sometimes neural networks, not gonna lie, have better ability than humans. Or like, no, the interesting thing about neural networks is that they can always come up with a solid prediction. Oh, that's definitely a plane. That's definitely a plane. Dinosaur is not a. That's a horse. Dinosaur is not one of the labels.
So what
You
is
can either
0?
have airplane, automobile, bird, cat, deer, dog, frog, horse, ship, or truck.
Oh, this might be a cat.
Oh yeah, that is a cat.
Oh my god. So scuffed. But it's fine. Yeah.
We didn't predict a cat. We predicted an airplane.
Yeah, it's kind of sad. And then I think you can just access the test data set. No, it's
Test labels, right?
yeah, test labels, and you can actually see what it is. I'm pretty sure this printed out correctly. Haha, what is 3?
Cat.
Oh, I got it right.
Yeah, but our model got 0.
Yeah, so the conclusion here is that you just need to train your model for a while more. Yeah, so it's like the conclusion is you need to train it for longer. The accuracy was like pretty good though, like 80%.
Well, that was on train. That was on train data set. Our validation, which is on our test, is like 60%.
Yeah, it's like almost guesswork. Or we can just do model.evaluate on train images, and this should have better accuracy. Wait a minute, this is not. It's on 0, 0. It's on. Hold up. Model.evaluate Oh. Model that evaluate inputs test loss and test accuracy.
You want to do model.predict?
Model.predict gives the other values, no? Oh, I can definitely.
I thought model.predict should just give you the output.
I think it was one. I thought it was evaluate. Oh, yeah. So now you just find the max of these. It's this one. Wait, it's actually pretty good. 1, 2, 3, 0, 1, 2, 3, 4, 5, 6. The sixth one. Is it actually that good? I'm surprised. Yeah. Okay, yeah. So we did it. We did it. And then now we can actually kind of see what it is. And images. It's a crab? Frog. I think it's a frog. Yeah, okay.
Yeah, it's frog. Frog is 6.
So that's basically all I have to show today. You can actually download it really fast. I don't know how it's downloading that fast. So yeah, that's basically. How did they get a picture of Catherine? Okay, yeah. So that's basically all. If you want to use this, I think. Can I just share this Python notebook with them?
No, just copy the code, paste it into our GitHub or something. I think that'll work better.
Okay.
You can export it to Python.
Okay, yeah. So that's basically all we have to show today. We basically showed, or we just kind of like explained different papers, which is all the different papers of the models. ResNet, AlexNet, Inception, transfer learning, and also like how to like make your own classifier, which is really kind of like a really simple task because you can just use TensorFlow. So that's basically it for this 5-part workshop where we learned how to implement neural networks from scratch, basically.
You want to introduce the final one of Keras, the code one?
Which one?
The code workshop next week?
Oh yeah.
For what competition?
So next week it's gonna be more of like an in-depth dive into TensorFlow Keras than just like this, just me showing you how to do this. And for this final, or for the competition itself, it's gonna like use a lot of what we learned about how to make the model and also how to like kind of train the model. So it's gonna be more focused on like the final steps, which is more on optimization. And on this optimization step, we're just gonna essentially introduce how to use TensorFlow Keras and like how to like just edit your model. And yeah, come to the reading group also. Do you want to add anything, Stone?
I'm good.
Okay, yeah. So that's basically it. Alvin, Catherine, do you want to add anything?
Survey?
Oh. Okay, just respond in chat if you liked the series. Okay, thanks, Jonathan.
Thank you, John.
Okay, so that's basically all. I don't think I have any other. Do you have any like questions or something about this neural network stuff? Wait, also we need to have a good meme. We need to have a good meme caption. Wait, Stone, should I put the meme caption inside the Discord and we can have someone come up with a good Zoom caption?
What?
You know how Steven put multiple Zoom things?
Okay.
We need a good caption for that because I want to post that onto Zoom memes for quarantine teens.
Okay, good luck. I need to leave soon, so.
Okay.
Thanks y'all for coming. Again, if you guys have any questions, you can also ask right now or ask in our questions channel. But otherwise than that, that's basically it. See y'all.
See ya.